All right, guys, so this is equilibrium part 2. You may remember last time what we did is we talked about the concept of equilibrium. Cam did a really good job of leading us to summarize the important things that you need to know about the concept of equilibrium. Those include the idea that at equilibrium, the rates are equal and the concentrations are constant. We'll put that up on the screen in just a second. Then, guys, we got into one of the do's of equilibrium, which was Le Chatelier's principle, the arrows that you just graded in homework. Guys, you've got to be able to do that on the test. Predict how reactions respond to stress, and that's Le Chatelier's principle. Today, guys, what we're going to do is the math of equilibria, and again, 15-ish minutes. We're going to talk about the math. We're going to set it up. We're going to solve 2 problems. You'll get your homework done. You ready to go? Okay, so guys, allow me to offer you this. Don't write this down, but offer you this as a place for us to regroup. So guys, this is right out of your notes from last time. We wrote down this equilibrium process. This was the foundation for the tube game that we played, and we talked about this idea. And if you're not sold on this, you may want to write, well, it's up to you. It's in your notes from previous. But guys, you should be able to answer this question. When a system is at equilibrium, what is equal? The rates are equal, as represented by the amount of water moving forward and back in the tubes. Guys, at equilibrium, the rates are equal. Do you want to explore that anymore? You're good? Okay, so guys, what about this? At equilibrium, what's true of the concentrations? We know they're not equal, but what are they? They are constant or unchanging. Guys, those are the 2 essentials that you need to know about equilibrium. Equilibrium is this magic set of conditions where a reversible reaction is happening at both directions at the same rate and at that moment, and for the rest of that reaction, guys, the concentrations don't change because they're perfectly doing and undoing each other. So guys, anything there you want to explore with the understanding this is really important. You guys good? Okay. So then you may remember we wrote this down in red. We just sort of jotted it down off to the right, and we talked about the idea that we've got this product to reactant ratio. For our tubes, it was 70-30 or 7-3. Frighteningly, when you come back for AP next year, many of you are actually going to remember that ratio because we do this demonstration again. And I'm going to ask you if you remember, and many of you are going to go, oh yeah, it was 7-3. We're really good at memorizing worthless stuff. So guys, here's what we're doing for the rest of the day. We are actually going to focus on this important product to reactant ratio. We're going to talk about how to set up these problems, how to solve these problems. So fundamentally, for the rest of the day, it's products divided by reactants, plugging in numbers and solving. Can we go forward? Okay, so guys, this ratio has a name, and this is where you want to start taking notes. Guys, this product to reactant ratio, it's up here in the subtitle. Guys, this product to reactant ratio is what is called an equilibrium expression, which is abbreviated K sub C. Guys, what you're going to find out, well, I know I keep saying this, but it's just unavoidable. We're coming to the end of the year, and for some of you, you're transitioning into AP. Guys, what you're going to find out is that this big letter K is actually the universal abbreviation for equilibria. And then C means concentration. You don't need to know that, but you're going to solve all sorts of K expressions next year. So this is called an equilibrium expression, and guys, it is, and you want to write down the definition, it is the mathematical ratio of products to reactants when a reaction is at equilibrium. So guys, generically, here's what these things look like. Kc is equal to, just as it says in the sentence, products divided by reactants. And guys, remember, those brackets are not parentheses. What do the brackets mean? You learned this when we solved pH questions. What do the brackets mean? Do you not remember? It means molarity, because these things mean concentration. So when we talk about amounts, we're talking about molarities. Now guys, the problem is that because the arrow goes in both directions, we really can't say this is reactants and this is products because it goes both directions. So we're going to say this: the products are always on the right and the reactants are always on the left. How you guys doing? Oh, good. Sam, I just had the opportunity to read your shirt. It's not bad. Oh, you got that. Got it. All right. Hey. So as it says in red. Yeah, so what that means is the numbers that you're going to plug into those brackets will be molarities. So think of it this way, David. What do we need to know about the products? The molarities. What do we need to know about the reactants? The molarities. And those are analogous to the levels inside the tubes. Okay, so guys, don't write this down. What's coming next? Don't write this down. But what I'm going to do for you is I'm going to model how to write a KC expression from this equation. So guys, please don't write this down. I want you to sort of put on your detective hat a little bit and see if you can figure out how to do these. So guys, here's what we've got. 4 moles of HF, 1 mole of H3BO3, remember the 1 is understood, and that yields 3 moles of water and 1 mole of HBF. Okay, what I'm going to do, guys, is I'm going to show you the KC expression for this, and I need you to see if you can figure out the rules for writing these things. So here you go. This is the KC expression for this reaction. And again, guys, don't write it down. What I want you to do is figure out how to do these. There are some important points that you need to keep track of. And guys, all we're going to do is write down the important points. I would propose to you that there's 3, although one of them is actually pretty obvious. So guys, what are you seeing? Given this is our starting point, what do we do to write KC expressions? First of all, what goes on top? The right side, right? And you've already written that down. But guys, but if you need that little guiding point, always start on the right. So if you're looking for steps or rules, always start on the right. So what's on the right goes on top, but again, you already wrote that down, so that's probably okay. So guys, what are the tricky bits that you see? There are 2 things that make these a little different. What about this? What do we do with the coefficients from the balanced equation? They become what? Where'd this 4 go? Right there, right? Guys, where did that 3 go? Right there. What do we do with the coefficients? They become exponents. You may want to write that down. Guys, the coefficients from the balanced equation become exponents. Then guys, what's the other thing that's different? What happens to the addition signs? What do they become? Multiplications. You do not add in the equilibrium expression, you multiply. So guys, if you can keep track of those 3 rules. Rule number 1, the right side goes on top. Rule number 2, the coefficients become exponents. And rule number 3, the adds become multiplies. You're going to be okay. You okay? Go ahead, Cam. Hold on. Here? Yep. Yeah. Neither. It would be a 3. Yeah, it would be an exponent there. Okay. You guys good? Because guys, literally, I told you we're almost done. We're almost done. All we're going to do is I'm going to give you 2 equations. You're going to write the KC expressions for them, and then we're going to solve them. So 10 or 12 minutes, and we're ready to do homework. So you ready to try to apply this? So guys, it goes like this. Write this down with me. These you do want to write down. So 2SO2 plus O2 in equilibrium. Remember, that's a double-headed arrow. These have got to be reversible. Yields 2SO3. So guys, let's apply our rules. And you're going to notice I'm going to skip some space. I'm going to write the Kc expression for this, but I'm going to skip some space. You don't need to. You'll see why in a second. But guys, here's what we're going to do. Right beneath this, let's write the Kc expression. Again, you don't skip space. You'll see why I am in a minute. But we're going to write the Kc expression for this. So guys, I'm going to step you through the first one. Then the next one that we're going to do in just a minute, I'm going to cut you loose. So guys, let's try this. So what goes on top? The SO3 or the SO2 and the O2? The SO3. So the SO3 is going to go on top. Are we going to put it in parentheses? No, put it in brackets. And then guys, what are we going to do with the 2? It's going to become squared. So would you agree that it should look like this? You okay? So guys, with that said, we've now got this other rule that we need to apply in the denominator. Because we know that these are going to be in the denominator. The 2 is going to become a squared. But what are we going to do with the addition? Multiplication. So guys, this is the Kc expression for this reaction. Given the rules that we've kind of figured out on our own last time, does that work for you? Okay, so now guys, do not write down the rest of this question, but I'm just going to give this to you. This is what you're going to see in homework. This is what you're going to see on the test. We will give you a balanced equation. You will write the Kc expression. Then we will give you some information about this reaction. And here's what we'll do. We will either give you all the concentrations and you'll solve for Kc, or we'll give you Kc, because remember we can look those up in a book. Guys, we can give you Kc and then all but one of the concentrations and you'll solve for one of those. So all we're going to be doing with these is algebra. So the question reads like this. Don't write it down. It says, if the final concentrations are SO2, boom, O2, boom, SO3, boom, what is the Kc for the reaction? So guys, we're solving for Kc. What do? Plug in the numbers. Do it with me. So guys, Kc is equal to, the concentration of SO3 is 0.20 molar. You're going to forget to square this. Guys, be careful of the exponents. Then in the denominator, you've got SO2 and its concentration. I don't like the way that worked out. Hold on a second. I think I can see if I can make this better. Hey, that's better. And let me grab this. Sorry, you can't see what I'm doing, but you'll find out it makes sense in just a minute. Hey, now our numbers are together. There we go. Okay, so guys, now we need the concentration of SO2. That would be 0.125 molar squared, and then the O2 is 0.11 molar. So guys, at this point, you need to grab your calculator. You need to poke that thing furiously. If you've got a TI calculator, I would strongly encourage you to either hit enter a lot or use parentheses. But guys, in either case, when you're all done, you should get the number 23. I'll give you a minute to play. If you don't get 23, you just need more time with your calculator. But guys, the answer is 23. Yeah. Good question. Let's let everybody get the number, but doesn't it look weird that there's no units on it? We'll talk. Because not only, Sam, are we going to talk about that, we're also going to talk about what does it mean. Did y'all get 23? Okay, so guys, here's the deal. If you got 23, good on you. If you didn't get 23, you just need to make peace with your calculator. And we're not going to do that now because it's an individual thing. I'm not the best person to help you if this isn't working, because I don't use a TI calculator anyway. I can help you if you want, though, with this one. But there's probably people around you that can help as well. But guys, I know this is wildly unsatisfying, but let's not do that now. Let's move forward. Let's talk about some questions that are already on the table. We'll solve one more, and then if you need calculator consultation, we'll talk in a minute. So guys, the first question, and Sam asked, is what are the units on this number? The answer is there aren't any. This is what is called the dimensionless number. All the molarities cancel out, even if they don't, because right now we've got molarity squared in the numerator and molarity cubed in the denominator. But we say that the molarities cancel out, and this is what is called a dimensionless number. But guys, understand, just because it doesn't have units doesn't mean it doesn't have meaning. Guys, what does 23 mean? 23 what? What is this a ratio of? What's in the numerator? Products. What's in the denominator? Reactants. 23 what? 23 times more product than reactant at equilibrium. Just like our previous ratio was 7/3, and that means we had 7 times more reactant than 3 times, or product than react. Our ratio was 7/3. Guys, this one is a ratio of 23 to 1. It means we've got 23 times more product than reactant at equilibrium, because that's what it is. It's a ratio. And guys, you need to be able to interpret that. So here's the bottom line. If Kc, and you want to write this down, if Kc is greater than 1, that means we've got more product than reactant. So 7/3, which is 2.3. That means more product than reactant. 23. That means 23 times more product than reactant. Now, guys, what if it's the other? What if we have more reactant than product at equilibrium? What will Kc be? What will it be? Can it be negative? Can Kc be negative? What are the numbers that lead to Kc? Molarities. Can you have a negative concentration? No, you can't have less than none. So guys, Kc cannot be negative, but it can be less than 1. Understand, those are not contradictory. You understand, right? You can be less than 1 but still be positive. So guys, if Kc is less than 1, this means that you have more reactant than product. So guys, questions? If not, we're going to solve one more, and then you're going to work on homework. You guys okay? Okay, so guys, let's do one more. I'm kind of kicking you out of the nest here. So guys, it goes like this. Here's your balanced reaction. This you do want to write down. But once you've done that, guys, just keep going. Write the Kc expression. I'm putting your homework answers on the wall, so we'll get together when that's over. Getting closer. All right. So guys, let's take a look at this. You should be able to do what I just asked you to do. You should be able to write the Kc expression for this reaction. So guys, when we do, we've got Kc. Again, I skipped the lines to write down the rest of the question. You don't need to. But guys, Kc, so the right side is going to be on top. These 2's become exponents. No. These 2's are part of the chemical formula. They do not become exponents, but what happens to the addition? Looks like this, yeah? Okay, remember brackets, not parentheses. Then, guys, in the denominator, we've got HI, and that too does become an exponent. That okay? All right, now, guys, allow me to you don't need to write this down, but here's the other type of question. In the previous problem, you were given all the molarities you solved for Kc. Now you're given Kc, and you're going to solve for a molarity. So read it with me. It says, if the Kc for this reaction is 0.39, guys, stop there. What does that tell you that the Kc is 0.39? Which will there be more of, products or reactants? Reactants, right? The denominator is bigger. Those are the reactants. That means that this is a decimal smaller than 1. Let's keep going. So, guys, for this reaction, it's 0.39, and the final concentrations of H2 and I2 are these. What is the concentration of HI? So, guys, let's solve it. We're given Kc. Plug it in. Yep. Products on top, reactants on the bottom. Right, oh, just always remember, do it backwards. It's right over left. Okay. So, guys, now we need the concentrations of everything else we're given. We're given H2, we're given I2. That is these. And then, as it says in the problem, what is the concentration of HI? I'm going to replace that with X, just because that seems easier to me. Do you guys remember that magic day in like 7th grade when you learned that you could, in math, replace anything with X? Did you feel like a little sort of God-like person? I can just put X for anything I want. Oh, yeah. All right, guys, so how do we solve this for X? What do we do? The second most, wonderful thing you ever learned to do in math. What do we do? Cross multiply. Have you guys noticed that everything comes down to cross multiplication? So we're going to multiply, and we get 0.39x squared. Let's resolve the numerator of the fraction. 0.2 times 0.18 is 0.036. Watching significant digits. Now, guys, how do we solve this for x? Divide by 0.39. Then take the square root. So, guys, when we get the square root, we end up with 0.3. But you'll notice this number has units. Now we're solving for a molarity, so we label it as such. So when we're solving for Kc, no units. When we're solving for a concentration, that, of course, is molarity. So, guys, there you have it. We are now doing homework assignment 4. Ooh, 8:17. Not bad, right? So, guys, you now have, we're out early, 40 minutes to work on your homework. The answers are already stuck to the wall. I see absolutely no reason why you can't get this done. If you need to talk to me about other things, I would love to be available to you. Cam, if you need my computer, stuff done.